Can you see my screen? Just show you op amps DC model.
Wait, how do I see? Oh, watch stream.
Yeah.
Okay. Yeah.
Okay, so you see Justin, you there?
I think you.
Yeah, I'm here. I see it.
All right. Okay, so do you understand the basics of what an op amp, the fundamentals of op amp? VP equals VN and IP equals IN equals 0. Do you understand what that means?
Oh yeah, there's no voltage difference between them.
You don't. Whatever VP is, VN is going to be. Whatever VN is, VP is going to be. So it's always taking the difference. That's very important when we get to near ideal and level 3 and level 2. VP equals IP equals IN equals 0. Why is there no current going into the op amp?
Because the voltages are the same?
No, well, technically there is current going in, but the resistance is supposed to be like gigantic. Resistance and Rn, you want it to be like infinite. You want it to be super large. So, see, here has 2 mega ohms. So you have big resistance. So there's hardly any current at all going through, going into the op amp. So that's the ideal. So this is what Dr. Russell starts the class with of ideal op amp. This is what you should be getting, and it helps with the math. It makes it simplified. So when we go to the near ideal and level 2, so this is what it looks like. See, right here, you would have a resistor, a gigantic resistor, basically making it open. And so you're having this voltage-driven voltage source, voltage-controlled voltage source right here, getting the voltage from VP and VN, but it can never be 0. It's a balancing act. You want it to be 0, but it can never be 0 because you want a difference in voltage. And then your mu is your gain. Gain will be from something a little bigger than 0, and goes to infinity. And then your IP equals IN equals 0. This will make sense when we see another model. This is the level 3. I'm not going to go into it as much. So just equations are just cut and dry for what Dr. Russell teaches. But if we go to the small signal model for the AC, this is where everything gets interesting. DC is fine and all, but AC is where all the fun stuff happens. Like I remember how I told you that this resistor is very, very large. That's how you get the difference in voltage for the voltage controlled voltage source. And your mu is going to be your gain. R out is going to be a resistor because it's going to have some resistance, but you want it to be as small as possible. So, and this is ideal. This is near ideal. This is ideal 2, and then what it looks like. Rn over R out. And this is for the high frequency stuff. I'm not going to go into because this is just very simple understanding of an op amp. All this here also is in your circuits 1 materials 8. So I'm not pulling it from anything else. You should also have the biasing methods from him. Can you tell me why this is wrong and this is right? For the top op amp?
If I remember correctly, I think one of them goes to the rails or something.
Which one goes to the rails?
The wrong way.
But why is that wrong? Yeah, sorry, go ahead.
No, I had nothing. Go ahead.
All right, look at the op amp. When you have negative feedback, like in the right way, VP equals VN, right? So you always want it to be equal to each other. So your negative so you have your input going into, say, positive side, and then your feedback is going into the negative side. So it's always getting the feedback from the negative side, so it always keeps subtracting from your input.
Mm-hmm.
So it will try to equal to each other. So what output will try to equal the input. It will always try to equal each other. This way here is your output's going to your positive side, and it's being added to your input. And it's going to keep being added and keep being added and keep being added while nothing's being subtracted.
Mm-hmm.
And so it'll hit the rails and just not work at all. It'll be worthless op amp. I'm not going into these. Okay, do you understand dual supply biasing?
No, I don't really remember this.
Okay, this was the older way of doing op amp. It's still viable, but with new technologies, you don't want two batteries. Two batteries cost double the price of one battery. But you have biasing is you're turning it on with DC. Like I said, everything's fun is when it's an a sine wave. When the voltage is up and down. That's when we get all the stuff we have today. But you need DC to turn it on. You'll cover this more in electronics too, a lot more, because you'll do it with transistors. But the op amp is just a collection of transistors. So you want it to turn it on. So you don't want to turn it on with AC because the voltage is always fluctuating. So you want it on with DC. So this here makes it a positive voltage, and this here makes it a negative voltage. These capacitors right here are just to remove any of the noise, any kind of AC signal, any kind of noise signal, whatever, because that will affect the power going into the op amp. And so if you remember what a capacitor does, a capacitor blocks DC, but it allows AC to go through, right? So these capacitors are to make any kind of like AC noise on this line go right to ground. It won't get to the op amp. That's all you're doing with this. So VCC equals VE, and then RGP equals the parallel combination of these two. That's so it's balanced. It's balanced to minimize the effects of IB, which we saw in the other slide. It deals with this. We want to keep it balanced, so the current won't be changing as much. Well, that's round one. Okay. And RIP equals RN. So these two are equal. And this is just like a more along of a differential amplifier. Now, single supply biasing, it's a little trickier than the voltage, than a dual supply, because these two batteries don't affect the input. They go right to the biasing terminals. Now, when you do you have to make sure your op amp can handle a single supply bias, and you have to read the data sheet to figure it out. These capacitors do the same thing. They keep the noise out of coming from the battery. These are also capacitors that keep the noise, keep the DC now from going into this side. These keep the AC out of the biasing, but these keep the DC from going into the op amp on your terminals. But where we have this is your gain equation, your gain resistors down here. But you have RGP1 and RGP2. RGP1 equals RGP2 if 2RF is equal to minimize IB, and if it's greater than, increase the input impedance to the positive terminal. and then these stay the same. And this is another variation of bootstrap voltage divider biasing.
Does it matter that the capacitors are polarized?
Good question. I do not have the answer to that off top of my head.
You said that the capacitors block the DC, but they allow the AC through?
Yes.
Okay.
So like here, the VCC battery is going to the positive terminal to bias up the op amp, but you don't want any AC going into this one at all. You don't want AC going to it because that will affect the biasing of the op amp because the voltage is changing. You don't want voltage to change on the biasing side. You want it to stay.
Is that why those two capacitors on the top right, they are fixed the way they are? They're not like in series because that's to block the AC instead of the DC? Is that what I...
No, it makes it so if any noise is on this line here,
Yeah.
it will go to ground.
Okay.
This keeps any noise from going on. These won't be in your calculations at all for biasing. None of these capacitors will be in your calculations for biasing. They're just there for AC side.
Okay.
So they just keep the noise out of the biasing circuit for the op amp.
Do you mind if I jump in a little bit for
Yeah,
that part? Yes. So as Bryce said, it does filter out noise, and I guess what he means by that is, let's say, high frequency noise in that voltage source. They get shorted to ground, so you would place those capacitors close to that battery. So that's what they do. So yeah, they filter out noise or high frequencies as well.
Yeah.
So ideally, you'll have a really stable DC voltage into your op amp.
And then these capacitors here keep the DC out of your input and output. They're called decoupling capacitors. Because here you'd want most likely an AC signal coming in, and you want to amplify that AC signal. So you don't want to have it. You don't want it like offset by a voltage, by a DC voltage. Do you get that?
Yeah, I think I follow. The VCC, that is a DC voltage source, correct?
Yes.
Okay.
All right. Here's ORCAD. I put on dark mode, guys, so I won't blind you guys if you're in dark room right now. This is a common amplifier, the LF365. You'll be using this one a lot in circuits too. I don't know much about Davis's labs for electronics 1. So do you guys remember how to calculate the gain of a op amp with just resistance?
Vaguely.
So let's do this. All right, so for gain for this will be, let me put it here. Let me create this originals sine wave. All right. Yeah, bias this thing now. I should have made this up before I started this. I think it's 10 volts is good enough for this. All right, so we want these to be equal, right? Let me get my calculator out. I'm gonna do some quick. Oops, sorry guys. I should have done this beforehand. All right, here we go. So I want this to be 3.3K. I'll leave that as 1K. And so this will be 767. All right, so what would my gain be from this? Anybody?
I'm just looking at the circuit, and I don't remember.
Yeah, don't remember the equation for gain?
No, like I see that R1 is connected to the output of the op amp, and I see that those two power sources are going in and out, but then it goes to that red dot, and I don't know if it's connected to.
Oh wow!
I'm assuming it's hopping over.
Good catch. That would have broke the whole entire circuit.
I'm like, man, this is confusing me. Okay.
There we go. Yeah, there we go. That would have broke the whole entire circuit.
That's better. You know, the terminals B1 and B2, I remember seeing them, but I don't remember ever using them.
No, you don't. That's why I grounded them.
Okay, gotcha. That makes sense.
So if we go back to no, it's not here. I'm not looking at. Oh, I don't have his stuff pulled up right now for that, do I? All right, right here. This is the equation for gain. It would be R2 over R1. But in this case, it would be R1 over R2. I just didn't put them in the right spot. It would be negative R1 over R2 oh, I'm wrong. I'm sorry. This is a non-inverting op amp.
I used to know what that means, but I don't remember.
The signal's going to the plus side of input, so that means it's non-inverting.
Okay.
No.
Yeah.
I see it.
But basically, the output should be positive.
Yes. So the
gain, sorry.
Yeah, so the gain for this one, let's see if I can find it. Where does it specifically say? He doesn't have it. Just it's minus this here. And now never mind. So the gain for the non-inverting op amp is 1 plus R1 over R2. So your gain will be 4.3 in this set. So if we multiply 2 times 4.3, we should have 8.6 on the output. So we just verify that. Oh, I'm hitting the rails. What did I do wrong?
Oh, add more voltage, like try 20 volts.
Right. Yeah. There we go. And so to verify, you would do measurement, a new measurement. So I would take max of voltages. Hang on, let me label these as V out. So I know exactly which one I could pick. All right. Max. There you go. Why? I'm sorry. 8.6. There we go. Does that kind of make sense to you?
I mean, what you did makes sense. What I always have trouble doing is coming up with the gain formula.
You can derive them, or you can just look them up. I looked them up.
The best way to do it is just look them up. Like, this is a difference amplifier right here.
Yeah.
So you'll have two. You have your feedback, and then you have this circuit. These resistors down here. So your V out. So you have this gain from right here, right? And negative R2 over R1 for V1. And then you'll have the this circuit. I'm sorry. R2, R1. Oh, I remember this problem. I'm sorry. All right, this is not a good example of what I was trying to show. I don't want to show Dr. Russell's questions because I don't know how he'll handle that. So the simple answer for the gain of the op amps will be for a non-inverting op amp, such as this, it'll be 1 over RF over R2. So this should be RF and R2.
Why do you call it RF?
Feedback.
Oh, okay.
And then for an inverting signal, So I'll just take this from here. And then I'll move it to here. And then I'll put a ground. On this. And then for the inverting, it'll be a negative RF. So 3.3 over 1K. So it'll just be negative 3.3. So now if we do the same thing again, run the simulation, it should be negative 6.6. Whoa. What did I do wrong?
What made you choose R3 to be that particular number?
Oh, because I wanted it to be balanced. Right here. Wait. So remove RIP and RN, right? So you want these two in parallel to equal GP, RGP, right?
So you calculated R3 based on what RF and R2 was.
Yes.
Okay. To
About 700
achieve that
ohm.
condition.
Yeah. So this one here, I am saturating it. And I shouldn't be saturating it. 17 volts. I think I broke something. What did I do wrong? Huh. This is dumb into a loop. I should have practiced one beforehand. All right, so
I think I know what's wrong.
what I do wrong?
Let's pretend R3 doesn't exist and it's just shorted. So basically, the other node 2, the inverting input, is grounded. So it's working as open loop, basically.
Oh.
So I think you need to keep RF there and then move R2 into R3. And I think that gives you...
Move what? Oh. Yeah, right. You are correct.
Yeah.
So, yeah. Wait. I put it where again?
Yeah, so put it there and then around the other side of it, and you would just remove R3.
So ground this one then, you said?
Yeah, you'd ground the other side of the resistor, R2.
Wait.
If I remember correctly.
No. Let me get my book out real quick.
What is a good book for op amps references?
Oh, I'm using my actual Circuits 2 notes.
Oh, the notebook. Okay.
Yeah, all the stuff I printed out.
I was about to say, I'm like, man, a book, that'd be useful.
I gave this book to somebody to use, and they reorganized it all. So now I'm set. Can't find what I need to.
No, actually, no. The previous configuration you had, it was correct. So I'm not sure what's wrong.
So PS3. Okay. Let me. Okay, so we got Y.
Oh, sorry. Put R2 between V1 and RF. That's where it should go.
Put R2 between where?
V1 and RF.
Oh, I see.
Yeah. Yeah, now it makes sense.
So, man. That's how it looks. Now we run it. It should be negative 6.6.
Nice.
There it is. So if we match that with the input, you can see the difference. It's 9 degrees. It's 180 degrees out of phase, and it's amplified. There we go. Do you guys have any more questions? Or Adrish? Justin?
Right now, no, but I mean, if I look through that document, I guarantee you I will have all the questions.
Okay, let me see what we have in circuits 2. Oh, no.
Is that correct?
I'm sorry?
I believe someone said they have trouble deriving the formulas for op amp equations. I mean, usually what I would do is just
Do you have a document? Because I know how to do it, but I don't have a thing to write it down with.
no, I don't.
Because Russell did it in class, and I don't have those. I stopped taking notes in his class. Actual deriving.
Just straight up stop.
But I mean, usually if I had to, I would just use KCL on the node VP and node VN, and then set it in terms of V output and V input, and get the transfer function that way. Usually using KCL.
Okay.
That's the best advice I got for you. And VP and VN are equal.
Right.
another one.
And we're for all these op amps, we're just assuming they're ideal, right?
Yeah.
Yes, you want to assume,
But
unless told
much
otherwise.
easier.
Okay.
Oh, he will last that too.
Great.
Could you do an example of that?
I don't have. I can't write on this computer. I'm not good with the Okay, well, let me see here. Let me open up. All right. This is. I don't know why that's. Ooh, whoa. What's my screen size? I don't remember my screen size. Yeah, okay, there we go. Big enough. Okay, or not. Oh, I see where I did wrong. Let's just zoom in. Okay, so we have the op amp, right? So let's do the inverting. It's the simplest kind of op amp to work with. And that just goes to VN. And V out, RF, RB. So this is VN, this is VP, this is VN, and so we know that's V out over VN, right?
Yeah.
Yeah.
So if we do the KCL for VN, it should be something like, you should get V out. So KCL is V out. Oh, how do I want to do this? I found my notes from circuits 1, so.
Well, the way I would do it is do VN minus ground, so current going to ground.
That's right. Yeah, there it is. Over.
And then, yeah,
RB.
over RB, yeah. And then
equals.
So current is going into the node still, since the negative input's infinite impedance. So it'll be, let's see, VO minus VN. So it'll be plus VO minus VN divided by RF equals 0.
I thought it'd be VO minus VN over RF.
Let's see. Yeah. You're correct. Yeah.
Yeah. No, I got it wrong. It should be. Oh, I'm looking at inverting. No, I'm right. Non-inverting. So let's just do an inverting op amp. It's a little simpler. The math's still simpler. That's where I messed up at. The math's a little bit simpler on non-inverting. I mean, an inverting op amp. So it would be, get rid of this. All right. So this resistor here, RB, and then here's your VN. All right, there we go. That's what I've got wrong. For your KCL, KVL. So it would be VN minus VN, that's confusing, minus RB over RB equals VN minus V out over RF. You see how that's done? And you know that, and there's a current here, IN, so you get plus IN. But IN should be 0, so just omit it. So you have the current going here, IF, which is this, and you have the current going here, which would be, say, IN. This would be IN. Does that kind of make sense to you guys?
Yeah. Throwing those currents in there really shaved off some rust.
Okay. Yeah, so by doing this, you can now do some algebraic gyrations, and you can get V out over Vn. And then that would equal negative.
Wouldn't the currents be in the same direction? Since the negative input is basically no current goes into it, so it has to only go to that. It has to go through RB and RF in one way. I mean, your equation's still correct though, so ignore me.
Unless I wrote it down wrong. Wouldn't put it past me.
No, your equation is still correct, I think.
Yeah, it still holds true. Yeah, I'm sorry. Yeah. Well, how I have it written down is this could be like minus IN. There. Now it holds true. These two go together and this, well, no. I did
there's
wrong.
There's no current going into it.
It's right here. There, now it's true.
Yeah. But your equations are still correct.
Yeah, this current goes in and these two currents go out. It's all how you label your currents. Make sure you don't do what I just did. And then now if we do a non-inverting op amp, so you have V out over here, and so we have V, F, RB, I'm gonna put RN here, and this is your VN, this is your VP, this is your VN, IP and IN. All right. So just the equation still holds true. V out over equals or V in is your gain. So we know that VP equals Vn. But Vn, the V negative terminal, is equal to V out times RF, RB plus RF. Someone's watching Disenchantment. All right. So these two equations are your KCLs. Well, this is Vn is just a voltage divider of V out. So it's this voltage right here equals this voltage. And because we know that Vn equals Vp, we can write Vn equals V out RB plus RF. And with some algebraic gyrations, we can get V out over Vn equals 1 plus RF over RB. And that's your non-inverting op amp gain. Do you understand that part?
Still thinking about it.
Or do you want to do the KCL way? This way's easier.
I don't know the KCL way. Oh, I do know it. I just don't like doing it.
It's longer. Like you just take advantage of the fact that that's a voltage divider, and it's much easier.
Do you guys need me to explain it to you again?
That would be great.
All right. So we know that the ratio of gain is voltage out over voltage in.
Yeah.
So if we look at it, and we know that ideal op amp Vp equals Vn, and Ip equals In equals 0.
Right.
All right. So we know from this part, this is non-inverting, so Vn is exactly the same as Vp. So it's right here. Because there's nothing else. It's just straight there. Same thing.
Oh yeah, because there's no voltage for Rn to ground. Right.
No, because just move Vp over here. Right? It's still the same voltage. Think of it as if you put a voltmeter here, and a voltmeter here, it's going to be equal because this is it's in parallel, kind of. So if you think like this, the voltage across here is the same voltage across here because it's the same thing across Rn.
Right.
So
Okay.
the voltage input is the same as the VP.
Yeah, all that the RN resistor does is adjust your input impedance because it'll be in parallel with an infinite impedance, so it'll just be RN. So input impedance in VN would be just RN. That's why it's there, but you don't need it necessarily.
Okay.
If it confuses you, you don't need it. But
Yeah, I can get rid of it completely. I like keeping it in because when you do equations, when they're not ideal, you want to have symmetry, and it can kind of give you can kind of get hints from that too. Dr. Russell loves to do that. So then we have VN is the same thing as a voltage divider. So if we have V out right here, going down from here, another resistor, and goes to ground. Here's VN, here's RF, and here's RB. Right? So you know the equation for voltage divider would be V out over this resistor over the combination of these two resistors.
Yeah, that seeing it in that orientation helps a lot.
Okay. So we know that Vn equal to the voltage divider of VO times RB over RB plus RF. And because Vn equals Vp from the ideal op amp, so we can write the equation like this. Vn, V input, equals V output times RB over the combination of RB and RF.
Because you're just substituting at that point.
Yes. And then you do some algebraic stuff right here, and you get this.
Just simplifying it, I guess.
Yes, that's all it is.
Okay.
Dr. Russell's famous thing of algebraic gyrations.
Why does he call it that?
Just Dr. Russell.
I also want to bring up one more point that may or may not be true. I don't remember, but you want to set that Rn and equal to RF in parallel with R. Yeah, to minimize the offset voltage of the output. But you don't need to know that.
Oh, the Rn, RB, RF in parallel?
Yeah, so you put Rn equal to that parallel combination of the feedback resistors.
Yeah, we went
to minimize the offset voltage. I think it's in those notes too.
Yeah, it's right. No, it's here. There it is.
Oh wait, I was right. Oh, nice.
Yeah.
Is that the same thing as balanced inputs? Or
It minimizes the offset voltage that you get at the output.
Yeah.
And the reason for that is because there's two input impedances technically. There's one going into the positive end and one to the negative end. If you calculate the one into the negative end of the op amp, you get the parallel combination. So you would just set Rn equal to that parallel combination, and that theoretically minimizes the offset voltage of the output. Does that make sense?
I don't really get it, to be honest.
Oh. It takes time.
Yeah, it takes a lot of practice to do any of these kind of problems. Like, I remember not liking op amps at all after Circuits 1, as like most people don't like op amps because it's a new concept. You go from resistors, then you start working with a first order differential equation, and you drop into a second differential equation, and you can understand that from calculus and diffie-q. But this, you're told, current doesn't go into it, but it amplifies the voltage. It's like, how? It's current does go into it, but it's so small. The engineers design it so that this input resistance right here, like we said, is so big that we want it to be infinity. You want it to be as big as possible. While your output resistance, you want no resistance. You want as little as possible coming out because you don't want anything to impede the voltage going out. But this is based off of the small signal model.
Why does it show that model as those two circuits separated?
This is a voltage controlled voltage source.
Right.
So you took electronics 1 with Russell. So if we look at the spring. No, wrong spring. Oh, where is it at? Op amp is just a collection of transistors. So let's go with the transistor. Oh, what is that? Do you remember which materials had the Miller model?
No. No clue. It should be in the high frequency response or whatever.
So that. Yeah, you're the Miller model, right? This is a BJT, and so an op amp is just a combination of transistors. But let's just to simplify it, if you took Dr. Russell's and you're taking electronics 1 this semester, you'll come over to the Miller model. So this transistor here, this whole circuit can be to represent this. RS, RB, RBB right here, RC, RE. These are coupling capacitors. Don't worry about them. They could turn to this. So when you're dealing with DC, this opens up, or if you're dealing with low frequencies, the capacitors there just kind of disappear, right? Let me see a picture. I kind of like this. This is just rearrange. This is another rearranged one, but these aren't touching. These are isolated now. But this is a voltage-controlled current source for BDTs, I think so, and it gets the voltage from this, from V pi, across these two resistors. I showed it. Let me see if I have it here still. So this is what it looks like. This is a simplified op amp. This is a current one. I pulled this from somewhere else. But we have 10 volts here, 10 volts going in. Let me change. Not from this one. So let me get rid of these. I want to see them. All right. Nope. All right. Here we go. This is a voltage controlled voltage source. So I'm going to put let me get rid of this. Let me change this up quick. So Here we go. All right. Where's R? There it is. So okay. So I want this to be gigantic. So let's go 2 meg. So I need to pull the voltage off of that. And so there. And let's put a resistor at RL. So you guys see how I made it? How it's not, it's technically, it's the same thing as this. But in real life, you have to somehow get that voltage to over here. In real world, you have to have you have to have lines coming up from there to measure off of, or you will never be able to get that. So if we have 10 volts here, I'm going to put a gain of 2 and run it. I have it set for bias. It's a 20. Okay, this is set for bias, right? Yeah, it's bias point. All right, so it's a gain of 20. All I'm doing is pulling the voltage across this resistor and then amplifying it by 2.
Now you have free electricity.
Yeah, that's what this model represents. So it's not touching in the picture, but when you run a simulation or actually design it on a board,
yeah,
you won't actually design it on the board because you'll have an op amp instead. But
because the next question would be, how would you build a voltage-controlled voltage source?
That's a whole other course altogether. You know how you here's a current source, right? You've seen batteries, but you've never seen a current source.
This is right.
That's something you learn in circuits. I mean, in electronics too. If you choose to take that, it's only taught in springs. Dr. Russell, we go over later on, right? When did we go over that? Current source, Amirs. Yeah. This is a current source. That's all it is. Of course, it's a very simplified and not a real world thing, but you bias a transistor and then you make it pull down a current, and that is your current source. We didn't get to do this because COVID happened at the last minute, and we lost a whole bunch of lab time.
Oof.
And I wish we would have stayed. I probably would have been better for me. But that's a current source. It's not like a battery. You can't physically have it. You can, but you have to have a whole bunch of other components to do it. And then we never got into the current control stuff. That's probably a part of another course altogether. I don't think UT even has that course. So you kind of understand op amps a little bit more?
Yeah. Yeah, so that helped.
So yeah, you'll get the same materials in circuit 2 as you got in circuit 1. So
be the same.
Yeah, the first part.
Oh boy.
The first part of circuits 1 is RLC design. Is RLC circuits, but in the S domain. So you won't have to worry about doing
Circuits 2, you mean?
circuits 2, which is all S domain. So you don't have to worry about time, because time is just too cumbersome. Then you go into name it. Then you go a little more into name and main and the S domain. Instead of using the what's it called? What do you call it? The
operator?
Yeah, yeah. You won't use that. You just be using S like Laplace now. And then you start going into op amps. So you'll go over biasing, the stuff we did today. You'll do a little bit of gain, but then you start learning about the transfer functions, because those go into like your biquads, your filters, also your oscillators too. So you start building up more and more, and you get heavily involved in op amps. And op amps are just two-port networks. You have an input port, and you have output port. So they're two-port networks. So you'll see it when you go live. It'll all start to click. Are you taking controls?
No.
I would suggest after circuits 2, take controls, because then it will, if you like this stuff, because controls, everything in circuits 2 made perfect sense in controls, because you learn about all the feedback stuff and all transfer functions and filters, even more not filters in a sense of it's high pass, low pass filters and band gap and all the other stuff, but you deal with all that stuff in the S domain, and it makes perfect sense if you pay attention to circuits 2. Controls is one of the easiest classes that I had. I loved it.
Really?
Yeah, it just made sense to me. Well, I'm a different type of person. I hate coding.
Yes.
So this kind of stuff really, really intrigues me, and I like working with it. I like learning about it, and that's why I'm going and probably continue my master's in this.
Did you take fundamentals to telecom?
No, I did not.
Okay.
It's a good class. If you like probability, you might like it.
Oh, well, I guess I'll stay away from it then.
Miriam, you came in late. Did you catch the first part of the, or when did you hop in?
When you were doing you and Carl were talking about the two ways to do the op amp.
This one?
Was it the longer way and the shorter way?
This one?
Yes.
All right. These were the equations to derive the gain.
Okay.
Okay. So this is an inverting op amp right here, right? Because the input is going into the negative side, and the gain, the ratio is V out over the input voltage. And if we know you have the rules of an ideal op amp is right here. That's the rules of ideal op amp. VP equals VN, IP equals IN equals 0. With those simple rules, we can follow the current through here, right? So current, let's do KCL on VN right here, right? On this node right here. So the current of IN is VN minus V input minus VN over RB. So that's right here. And then IN is going to 0, so you don't have to worry about it. So that's leaving the node. And then this current is VN minus VO over RF, right here. And then you just do algebra to get VO over VN, and you'll end up with negative RF over RB for a inverting op amp.
Okay.
So the inverting one is the simplest one. And for non-inverting, we have to use those rules we talked about earlier. VP equals VN, and IP equals IN equals 0. So VP is the same as VN. VP right here. I'm sorry. V input is the same as VP. And then VN is a voltage divider. It's V out times RB over the combination of RF and RB. So right here. And because VP equals VN, we can write it, we can substitute VP for V input equals V out times the voltage divider network. And then doing some algebra, you can get V out over VN equals 1 plus RF over RB.
Okay.
So that's it, and that's the non-inverting gain equation for an op amp. And if we go to PSpice, this is the setup for an inverting. So I have 3.3K here, a 1K resistor. So this is RF, this would be RB. This is the balance transistor, the balance resistor. So we have 2 volts going in. So if we run the simulation, red is your input, green is your output. Green is here. It's inverted, right? 180 degrees. And it's 3.3 times greater than 2. So if we go measurement, turn that on, it's 6.56. And if I do the maximum of this one, nope. Picked the wrong one. So max. Wait, why wasn't that? No. Oh man. Sorry. There we go. So you have 1.999 times 3.3, you get 6.56 whatever. So you kind of get the... So the simulation is just to verify that your math that you do analytically on paper is correct. If you run the simulation and then you get a completely different number, then you know you did something wrong on either building the model or your math. So it's best to look at your math first, make sure you did it right the first time, because just don't hop into PSpice or LTSpice and just build a circuit and hopefully get the right answer. Because if you don't know what you're supposed to get on your simulation, you don't know if the answer is right or not. So it's always important to make sure you do your math first and then do simulations to verify your answers. Because you'll do the same thing in the labs. Dr. Russell, you cannot do the simulation because you don't have the answers to the resistors. The labs for circuits 2 you have to do the pre-lab before you even get to the lab, or else you'll never finish the lab. Because Dr. Russell does not give you the resistor values. He might give you one value, but you have to use the equations from the homework and the notes to find the resistor values of the other ones. And then he just gives you a hodgepodge of resistors and says, find them. So don't go in there and say, I can do the lab during the lab. You have to do them. You have to do the pre-lab. Yeah, Carl wrote down the KCL.
Oh, this is for the non-ideal case for the op amps.
Oh, non-ideal. Okay. Let me. Okay. So you guys kind of understand it a little better now?
Yeah, a little.
Can I ask you, Miriam, do you know why? Just to see where you're at.
Wait, but so like in the paint, non-inverting.
Right here, yes.
Yeah, that's for non-inverting.
Yes.
And then the simulation was inverted.
Yeah, I did the other one beforehand, and I just don't want to take the time to quickly go back to it.
Oh, okay, I was making sure.
Yeah, this is a non-inverting op amp right here. Now,
I will
upload this to YouTube, the IEEE YouTube, and so you can watch the rest of the lecture, not lecture, but the video before you got here.
Okay, yeah, that'll help. Did you put the link in the chat?
For what?
For the IEEE YouTube, or do I just look up IEEE YouTube?
Do that now.
And this is review for circuits 2, right?
And electronics 1, because they had questions about op amps. And I think David starts on op amps.
When I took him, he started on diodes, I think.
Oh, he did? Because a lot of you started on op amps.
Oh, cool.
So that's the link to the IEEE YouTube.